Aloha, everyone. I'm Frank. I'm getting the opportunity tonight to introduce the speakers. Welcome if you haven't already heard this twice before, because it seems like the room has not changed a bit. But I'm fortunate to introduce Dr. Tom Schad. His subject is how to take 500,000 pictures of the sun every day. So try and do that in 15 minutes. Please welcome Dr. Tom Schad.
Oh yeah, you need this. Sorry. All you gotta do is, it's good to go.
I can't see myself. Do I look ridiculous or not? Well, welcome everyone. Thank you for coming to my talk. I'm excited to have this chance to really tell you about what we really think is a really exciting project going on here on our home of Maui, and that's the Daniel K. Inouye Solar Telescope, which is of course under construction on Haleakala. And as I go through this, I want to show you kind of the nuts and bolts of the observatory, kind of give you a tour of what science is going to be done with the telescope and really how it operates on a day-to-day in terms of its instrumentation and how it takes photos. But if I fall short of that, which it's only 15 minutes, so I will fall short of that, please do go to this website, dkist.nso.edu. This is just dkist. This is on the National Solar Observatory website. National Solar Observatory is located here and also in Boulder, Colorado. And they have a really nice website with up-to-date photos and information about the telescope and the science goals and everything of it. So DKIST is a large cog in a mission that serves humanity to protect our environment from space weather. This is one of its missions, and it fits in an overall picture that's in space, actually. So this is a summary picture of all the spacecraft that we have in space, constantly observing pieces about our magnetosphere and our heliosphere, and how activity from the sun comes in and impacts our earthly environment and controls how our electronic grid operates, and it affects our telecommunications and our other satellites. So it's a really critical piece of how we control our modern day society and our modern day life and protect it. And we've known for many years now that the sun goes through these cycles. They average about 11 years in length. And what happens is the magnetic activity of the sun waxes and wanes. So in this composite image from a spacecraft, you can see what's basically million-degree hot gas. And back in, this is only 2 years, but you can see that in 2010, it's the activity that's going on is actually kind of small in comparison to just 2 years later, you have all of this hot gas all over this place. And this is a cycle that happens every 11 years with the magnetic activity. But DKIST, its place in this is actually to get at the detailed physics of what's going on in this magnetism and how energy is enters into the atmosphere and how it's dissipated and then ultimately eruptively released in solar flares and storms. So for us, the key questions for this solar telescope, have a seat, yeah. You can take this one if you need. The key questions for us are really physical ones, more than just monitoring. A lot of these spacecraft monitor things. We're trying to get at the physics of it. So our questions are kind of what controls this variability that affects the technology? What leads to a sunspot? How is the atmosphere heated? What generates the magnetic fields? How are they destroyed? And then what role does the magnetic field of the sun play in energetic events? To answer these questions, we have to understand both the large-scale sun on how it evolves, but also we've come to learn that it involves us in a science of the tiniest details. And that's where this telescope comes in. So how do we do this? We study the tiniest details with great effort. And one of the details that we look at any telescope is the spectrum. If you're used to looking at spectroscopy of stars or anything, you know that the sun, if you enter it into a prism like there on the left, it breaks it up into the colors of the sun, of the star. And this is a high-resolution spectra of our sun, showing you the different spectral features of magnesium and hydrogen, so you get a feeling of what kind of gas is in the sun and what also the physical conditions that gas is in. So the width of these lines tell us a lot about the temperature and the density of what's going on in the sun. The depth of them also give us different ideas of the layering of the sun. So we look to these spectra to understand the tiniest physical details, but spatially we look at it also in quite detail with images. So if you take one of those spectral lines, in this case an iron line, and you look in the core and you look at very, very high resolution, this is one of the highest resolution images that we have to date. This is what the area around a sunspot looks like. So we have a large sunspot here, which is a concentration of magnetic field, and then you have little pockets that are called granules, which are about the size of Texas. I'm from Texas, so I can say that. It's not the size of Alaska. Sure, they're bigger. But they're about the size of Texas. And also embedded in all this, you can kind of see some tinsel, really, this little bright stuff. This bright stuff is actually revealing what the magnetic field is. So if you take a special picture of the sun in polarized light, much like you do polarized sunglasses on a day when there's a lot of glare coming off of cars and things, you can look at the polarized light and you can actually measure the magnetic field in the sun. And this is what we've been doing for about 50 years. So this gives you a map of what the magnetic field is doing on the surface of the sun. White is saying the magnetic field is coming towards you, and black is the opposite. But this picture that's on the surface looks a lot different as you just jump a little bit of height up as the density falls. So above this magnetic field, you go up a little higher, and all of a sudden the intensity looks different. The sunspot starts to get little spikes out of it. This magnetic field energy comes these little bitty hairs. These are called filaments and fibrils. If you go into hydrogen, this is what a hydrogen picture looks like at very high resolution, of all of these hairline things created by magnetic field coming out of the surface and expanding as the density drops off. If you go into a calcium line, it looks a little different, but it's about the same picture. Calcium, you're looking at gas about tens of thousands of degrees Kelvin, or Fahrenheit's about the same. If you then jump up just, again, a little bit higher in the atmosphere, all of a sudden things go really crazy and the temperature jumps up to 600,000 degrees Kelvin, million degrees. And this is one of the persistent mysteries of the sun, is exactly what controls this temperature and this energy in the atmosphere. What takes the magnetic field energy that the convection of the solar rotation is generating and creates this heat? But these are all static pictures. This would be too easy. We could take pictures of this, I mean, take one picture, you got all you need. But this is all dynamic, of course, so if you look at a short movie, oh, there you go. It's not going to let me do it. Yeah. If you look at a short movie, you can see all of the hairlines. Unfortunately, it's not going to work. You can see all of these hairline features oscillating back and forth and waving back and forth. And you can see the motion of the gas below churning and just injecting energy all the time in the atmosphere. And if you go higher with really fancy instruments, this one is in Sweden, and you pick out just the hydrogen gas and you look at the limb, you can actually see that it's raining on the sun. So this is a really neat movie where you actually go through a spectral line. So at the very beginning of this movie, you're seeing the surface of the sun, but then you get deeper into the spectral line, and you get to see the hydrogen 10,000 degree sun, and then you get to see all of this material raining out of this hot corona. It's cooling off like rain. So this kind of dynamics is going on all the time on the sun. So this is giving you a picture of really how we study this type of activity from DKIS. We've looked at images, we've looked at spectra, we've looked at some polarization, not a whole lot yet, but we've looked at dynamics. The next thing is really polarization. So if you go to this outer atmosphere of the sun again, and you look, this is again one of the spectral features that I showed you in the spectrum of the sun. What this movie will show is it'll basically show you what the sun looks like in different pieces of this energy that the sun is giving. This is going to show you the structure, but then these are going to show you particular patterns that the magnetic field creates in our data. This is the kind of stuff that we're looking for at DKIST. So if you go through, you can see the fibrils on the left, but then you get to see all of this pattern. I'll play this a couple times more. And what these patterns are again, a special parapolarized sunglasses that we're looking at the spectra with. And this type of polarization, there's different types of polarization, but this type of polarization tells you a lot about what the field is doing in the direction towards and away from you. And this type of polarization is telling you what it's doing in the other plane. So you get a full vector map of what the magnetic field is doing in these kind of things, in this type of data. So what we've come to an impasse, though, in many ways, because we've learned enough through all of this advanced data that we know that to understand solar magnetic field magnetism, we need high spatial resolution, we need high temporal resolution, we need spectral resolution, we need a lot of different spectral lines, we need a lot of polarimetry. But to do that, we need great tools and we need great people, and that's what really this project is about. So this project is about 15 or 20 years in the making. It's Daniel K. Inouye Solar Telescope, once called the Advanced Technology Solar Telescope, under construction on Maui. And just as of this afternoon, about 2 hours ago, this is what it looks like. We're very excited, so it's really coming into its being. So you can see the dome up top is not quite closed in, but a lot of what the shutters are, where the light is going to be directed in, are in place, and a lot of the building is already there. And this is all the work of really great people. These are two of the lead engineers, the people doing the thermal systems and the mechanical systems, up doing a test this day on these big girders that went up for the dome on this particular day.
How tall is it now?
Actually, 137 feet. Yeah. So to give you a scale, obviously the telescope's bigger than these people. This is a person right there. So it's pretty big. And Rob Grukowski, a local amateur astronomer, has taken some great photos of this construction at night. So this is the Milky Way behind the DKIST. Beautiful photos. So if we want to get into the nuts and bolts of it, what is it? This is a telescope. So you have a primary mirror where the light comes in, and the light is directed through a system of fold mirrors back down into basically a laboratory. But it all starts with a mirror. This mirror is big mirror. It's a big mirror for the solar physics world. It's 4 meters in size. Here's a picture of it undergoing testing in University of Arizona in Tucson. And it's 4 meters primarily because of two reasons. Again, it's to resolve the smallest magnetic elements of the atmosphere. But then the second one is to collect enough light so that you can actually resolve those magnetic fields. You need enough light in a very short amount of time in order to even see these little details. So you need all of that light. So there's really two purposes for the size of it. This is a picture of testing where they're actually grind polishing the mirror, so it's putting the precise shape. You have a roughness of this mirror of about 2 nanometers, so it's really, really fine scaled. But then the mirror itself sits on what's called the telescope mount assembly, which is this big mount. This is already built, even though it's not in place up on the mountain, but this is what it looks like in a factory in Illinois. This is, again, you can see the people on the side. And this is an impressive feat of engineering because it can point so precisely at the sun within about a half arc second controlled, but then it also has a whole system of pipes coming up the side that takes away all of the excess heat of this huge solar beam coming into the telescope. Because we can only look at a little tiny piece of the sun because it's otherwise too hot. We can only look at about 5% of it. Quick question.
Don't want the heat bending the mirror, ruining your mirror.
Exactly, yeah.
How will that get
So the engineering process goes, they design it, they construct the pieces, they construct it in this in the factory, they do all of the testing to make sure it's precise, and then they take it apart and they ship it. And then we put it together all again, because the time on the mountain is such a precious thing that everything is efficient and everything is built beforehand before it even goes up. So a lot of the components of the telescope are already built, sitting in places or being tested. So another component is underneath this big telescope mount assembly, there's this laboratory. But because the sun rotates throughout the day, we actually don't want the sun to rotate in our images. So we actively derotate the entire laboratory so that we take out that rotation. And that's this whole lab. So all of the instruments in here and all of their electronics, about 20 tons of material, are all rotating on a bearing. And this is in the laboratory in Illinois again. And this is a movie. So this should show it rotating. This is rotating at fairly low speed. But basically, all of these racks have electronics on it, and on top of this is going to be the instruments. And then all of the cabling goes up through this. Again, this is something that is built beforehand and rigorously tested in the lab. This is big concrete blocks sitting on top of this lab pedestal to make sure that this thing doesn't bend when we put the weight of instruments on it. So this is a critical piece. Next is the instruments themselves. So again, down in this area, we have 5 instruments being built by various partners across the world. So it's really messy. There's a lot of, this is 60 feet across, but it's really a lot of space is already taken up by instrumentation. And this is 5 instruments. If we take a top view, you can see them a little bit better. This is an instrument called cryo-NIRSP. This is a visible instrument. This is another instrument called DL-NIRSP. There's 2 broadband imagers here. There's an adaptive optic system and a visible spectrograph. This is all sitting on this 20-ton platform rotating all the time. Again, because we want a lot of different diversity in our data. We want imaging data, we want spectral data, we want time data. We use all of these instruments simultaneously. And to do that, we basically divert the spectra in different directions. So we take that spectrum again and we send all the red light one direction and all the blue light the other direction. And that's done with these huge beam splitters. They're called beam splitters or spectral splitters. They're about this size. And we put them in different configurations so that we can use the instruments in different ways for whatever the scientist wants to use. So again, this is that picture of the instruments. So the visible tunable filter, this big box here, is being built in Germany. These 2 instruments over here are being built in Boulder, Colorado. And then these 2, this one here and this one here, are being built down this hallway by the University of Hawaii. So the title of my talk was, how do you take 500,000 photos of the sun every day? So here's how you do it. You have cameras, a lot of cameras in all these instruments. So these instruments have up to 3 cameras apiece. But these are big scientific detectors, so 4K cameras in many cases, so bigger than your TV. Or if you have a 4K TV, then that's the size. It's a little bit bigger than a 4K TV, actually, because 4K TV is not actually 4K. These are actually 4K cameras. But here's the kicker. Each one of these cameras can take up to 30 images every second. So when you have up to 11 cameras working at the same time at 30 images a second, you get a lot of data, right? So this is one of the big challenges, the engineering challenges of the telescope, is what to do with all of this data. So if you look at the different instruments and different spacecraft over time, you can see how much data they produced as a function of time. This is those beautiful ultraviolet images I showed you at the very beginning of the sun in time waning. That mission takes about 12 images a second, and they're smaller. We're taking 11 times 300 images a second, and we're doing it for a lot longer. So this is a log plot, so you can see that this is a multiplying by 10. So this is how much data we're getting, or expected to get, from the mountain every day over time. So your phone is down here, your laptop is about here. Times 10, times 10, times 10, times 10, you're up into petabytes, is what it's called. We're getting petabytes. So this is how you take 500,000 pictures of the year, 500,000 photos of the sun every day. But beyond just the incredible engineering that's gone into this facility, the exciting thing is to get at the magnetism, and this is what I, as a scientist, am really excited about. To get at pictures of this and actually understand that these little fibrils are magnetic fields that produce a certain amount of energy that heat in a certain way and reconfigure themselves in a particular way that create flares, and then we can predict them. And that's where we get back to the solar cycle and the space weather and understand really how to protect our human environment, but also use this knowledge for other stars and understand what other cycles are going on in other stars that might be interacting with perhaps other civilizations. You know, this is what this facility is about. So DKIST is a tool, I think, for the future, and it's a tool for our world. Everybody's excited about it, and I am too. But just to really quickly advertise two things I want to say. Sorry, I'll take a few, 1 minute. You might have seen some posters hanging around about a partial solar eclipse. March 8th next year, 2016, there's going to be a partial solar eclipse. You should read the news. We'll be planning things to observe this. It's going to be really nice from Kihei and the West Coast. It's going to be an afternoon event, so it's going to be maximum about 5:40 in the afternoon, right at sunset. So this is a simulation of what it's going to look like on the horizon. So it looks like a moon. Exactly. It's going to look like a crescent moon. And for any students or kids you might have, we're also planning things that we're going to get information out to teachers soon. As a part of this eclipse experience, we're actually creating about 20 or 30,000 eclipse glasses, so that any student on the island who wants to enjoy the eclipse, they can. And as a part of that, we're hoping to get students involved with creating the art that might go on the glasses. So we're getting this information out to teachers next week. But basically, we're looking for a student on Maui to create their own design for these glasses, and we're going to put their design on the glasses and distribute them. With that, thank you so much for your attention. And if you have any questions, I know this was very quick, but if you have any questions, I'll be just down the hall at the poster, and feel free to stop me.